Okay, so to save us a little bit of time there, I have gone ahead and run the numbers there for, you can see the volumes there. So V1, we said that was given 600 cubic centimeters. I went ahead and converted that to cubic meters, just simple conversion. That's also V4. And then, again, by definition of the compression ratio, the Vmax, that's V1 divided by R, gives me the min volume. And so these are the min volumes, V2 and V3. So that we've got those now, okay? All right, what else? Again, what are we looking for? We're trying to find the temperature and pressure at state 3. Now, we could use ideal gas law possibly to get us there. Here's what we know. We know all three of these properties at state 1, okay? I know the volume at state 3, but I don't know pressure or temperature at state 3. So I can't use ideal gas law alone to get me to state 3, to get me to P3 and T3. I need to know one or the other. I need to know P3 or T3. I could use ideal gas law to get the other one. So I need to find something else, some other way of trying to get from one state to the other, or one property to the other. And we say, all right, well, what else do we know? What else links to state 3? What do we know about state 3? Well, the volume, that's constant, and we've already said we know ideal gas law. But what about this? That's on my screen, right? Loud pop here, sorry. Yeah, so the entropy at state 3 is equal to the entropy at state 4. It's an isentropic compression to get me between those two states, right? So how does that helps me somehow, right? How does that help me? Well, if we make what we call the cold air assumption, meaning constant specific heats at room temperature. That's what the cold air assumption means. That's a common thing we can do in these types of problems. So I make the cold air assumption. If I assume constant specific heats, and whether I make that assumption or not, these isentropic states, because it's an ideal gas, and because it's isentropic, this is in the Changle and Bowles textbook, you've got these isentropic processes for an ideal gas. If it's for any process, there's the Gibbs equation. Gibbs equation simplifies down to what I call the K ratios if I've got an ideal gas undergoing an isentropic process. Here, because it's an Otto cycle, it's an ideal gas, in between states 3 and 4, it's isentropic. Notice I know T4. So what you can do is between states 3 and 4 and between states 1 and 2, you can use these expressions. This serves as your second law, right? And so between states 1 and 2 and states 3 and 4, we can use these expressions, okay? So now this is, and we could use this to find either pressure or temperature or both, but notice this says here T2 over T1 is equal to V1 over V2 raised to the power of K minus 1. Okay? Well, here's the thing. This says 2 over 1, but you could make this box over star as long as you say this is equal to star over box on this side, or dog over pony is equal to pony over dog on this side. Whatever subscripts you want to use. Here, we're going to use subscripts 3 and 4. Right? So again, for an isentropic and, important and there, since it's isentropic and an ideal gas, we know that T, and I'm not going to use 2 and 1, I'm going to say T box divided by T star. I'm going to use subscripts of box and star, or use X and Y if you prefer, is equal to the ratio of V star over V box. These are not speeds. These are specific volumes. Remember how we derive these expressions. And that is raised to the specific heat ratio K minus 1. Now I've used box and star here to just, again, emphasize, put whatever subscripts here you like, as long as you put, in this case, we're going to use 3 and 4. So if I put 3 here, I use 4 there, as long as I put 4 there and use 3 there. Okay? Let's talk about the K value. Again, if we make the constant, we make the cold air assumption, assuming constant specific heat at room temperature. What that means then is we just go pull, this is the table, this is room temperature, 300 Kelvin, specific heat of various gases. We're going to use air at room temperature. This is the only time, typically, that we use this table unless we happen to have a really cold process. Most of the time we use this table, right? Some of you guys have lost a lot of points on that. Most of the time we use, am I on the screen there? Yeah, most of the time we use this next page, right? We use the properties out of here, at least if you want all the points you do. But in this case, we can kind of cheat a little bit and use at room temperature because we're making the cold air assumption. So if you're making the cold air assumption, what that means then is that for cold, what we call cold air, K is equal to 1.4. And let's go ahead and get C sub V. We will possibly need that later. C sub V for air is 0.718 kilojoules per kilogram Kelvin. Let's go ahead and get that just in case we need it. We also know the R value is 0.287, I think, right? Yeah, 0.287. We do have the ideal gas law up there. We might need this guy later. Okay, so we've got that one now, just in case we need it. So there's my properties. We've got those handy thermal properties for cold air. And again, we're okay doing that because we're making the cold air assumption. Okay, so again, what are we trying to do? We're trying to find T3. I know T4, and I know the ratio of volumes, right? Notice that this is, if I say that this is T3 over T4, then is equal to the ratio of specific volume 4 over specific volume 3 to the K minus 1. Now one might say, Steve, we don't know the specific volumes, we know the total volumes. And that's okay. Yes, we do know the total volumes. Now here's what you know. You know this is V4 over the mass because it's constant mass. And so the specific volume at 4 is V total volume divided by mass. And that's divided by V3 divided by mass to the K minus 1. So note that the ratio of specific volumes, because the mass is constant, is also the ratio of total volumes. And again, remember, V4 is a maximum volume and V3 is a minimum volume. So this is simply the compression ratio. V4 over V3 is the compression ratio. And again, because the mass is constant, specific volume 4 over specific volume 3 is also equal to the compression ratio. So this one's pretty easy, right? T3 is going to be T4 times the compression ratio of 9.5 to the power of 0.4, and you can substitute in here 800 kelvins, because that was T4. 1.4 minus 1. Okay. So pull my calculator up here. Make sure I don't have a glare. You're going to hear pop, sorry. Okay. Make sure we don't have a glare there, so we can do 9.5 raised to the power of 0.4, and then multiply that by 800. It's going to be a huge value, as it should be. That is the temperature after we've injected all of this heat that represents the combustion process. I'm getting 1970 roughly kelvins. We'll say 1968.7. That's a little too precise, but we'll go with that. That is higher than T4, and I would suspect that's also higher than T2, so I think that's safe to say that that is my max temperature. Okay? Alright, now, if I knew the pressure at state 4, I could use one of these K ratios. There's a K ratio for ratio of pressures to ratio of volumes. If I knew the pressure at state 4, I could use that also. I don't know the pressure at state 4. I could probably find it, because I know pressure at state 1, but now that I know now that I know temperature at 3, I can just as easily use state 1 and state 3 to find the unknown pressure at 3, and that's one fewer step. So let's do that. Again, why? Well, because I need max pressure. I need P3. Okay? Alright, so this is page 1. This is L25, page 2. For me, that's page 2. I don't know what, I'm hoping you guys are taking notes. These videos are probably pretty boring if you're not taking notes. But anyway, you guys have had all semester to figure that out. I hope you have. Let me know, by the way, if you haven't done the course evaluation, let me know how it's going and what you like and what you didn't like. And I'm not a big fan of the online stuff, but I'm hoping you guys are getting through okay. Okay, what are we trying to do? We're trying to find P3. Okay, now thank you for letting me get organized there. Let's find P3 using the ideal gas law. So P1 V1 over T1 is equal to P3 V3 over T3. I know T3 and I know V3 and V1 and P1 and T1. So we're trying to find P3. P3, and I'm going to group the like terms together. So P3, solving for that, that's going to be V1 over V3 multiplied by T3 over T1 and then multiplied by P1. Again, my preference is to write ratios of the like terms. So put the volumes together, and again, notice that is a compression ratio. That's a max volume over a min volume. Multiplied by, again, T3 over T1, which we know those values, and then multiplied by P. Okay. So now we can actually find the number here. So this is 9.5. That's the compression ratio. Okay. Oh, I shouldn't have cleared that. That's okay. Multiplied by T3, which is 1968.7 kelvins. And then what is T1? Normally I will, when I'm in front of a class, I'll say, okay, what is T1? And I'll wait until somebody says 35 degrees. They'll say 35, and I'll say, okay, so what is T1? Because you can't use 35. It's 35 degrees C. Right? It's got to be 35 plus the 273. We've got to use Kelvin here. This is 308 kelvins. And that's what we're going to use for T1. You have to use absolute temperatures here. It's an ideal gas law. Even though it looks like Celsius over Celsius would work, no, you got to use kelvins there. And you also got to use an absolute pressure here. There's no reason to assume that 100 kilopascals is not an absolute pressure. There's no reason to assume that's a gauge pressure. But if you do have a gauge pressure, you can't use that here. You'll have to convert it to absolute, just like you got to convert the temperatures. Okay, let's just do 9.5 times 1968.7 divided by 308, and then multiply by 100. All right, and that's going to be in kilopascals. That is, we're going to say 6. I'm going to go and convert to megapascals. It's going to be 6.1 megapascals using ideal gas law. Again, they've asked us for 4 things here. They asked us for the maximum temperature and maximum pressure. That's going to be my second answer. So I got 2 answers now. Now they want us to also find the heat in. They want us to find the heat in. If you're like me, it's like, where heat in? What the heck is that? Well, that's a good place to stop, I guess, isn't it? All right, we'll pick up the next video because I'm about to hit 15 minutes. See you guys in a second.